An electrophilic aromatic substitution reaction called halogenation is a reaction in which you take a benzene ring and you treat it with elemental bromine and a Lewis catalyst, iron tribromide. And when you do that, you are going to generate a bromobenzene. Now, go back to some history lessons. What if we try to do this reaction? Well, let's do it this way. What if we try to do this reaction with just elemental bromine? You would have no reaction. You need to add this Lewis catalyst to get this to go. And what you're going to see in a moment is that this Lewis catalyst is going to generate a very strong electrophile. And if you go back to my video for the general electrophilic aromatic substitutions, you will recall that I said that we are generating strong electrophiles. And so that's what this iron tribromide is going to do for us. So that's the overall reaction. Now, how do we do it? How do we go about that? Well, the first step is we're going to just focus our attention on those species right there. Okay, so let's draw it out here. So if I extend out, draw a Lewis structure here, making sure I did cut it off. Let's do it like this, actually. I'll just draw it like this for simplicity's sake. And then we have our elemental bromine. Our elemental bromine, I'm going to expand out. Okay? And we know that bromine is going to have 3 lone pairs on each of the bromines, like that. And so what's going to happen is one of the lone pairs on the bromine is going to come in and attack the iron atom, like that. Okay? And that is a reversible process. We call that a coordination step. A coordination step right there. And that's going to give us a species that looks like this. Okay? We have our iron, the 3 original bromines, and then the new bromine. Now look at what's happened here. We have a halogen with 2 bonds. And so when that happens, that's going to, wait, let's draw in our lone pairs so we can see those. Okay? And so that's going to make that bromine positively charged. And then that's going to make the iron negatively charged, like that. And then the next thing that's going to happen, also a reversible process, is the heterolysis. We got it all in there, okay. Heterolysis, heterolysis, I've heard it both ways. So what's going to happen now is that we're going to break this bromine-bromine bond right here, okay. And when that breaks, let's follow the electrons. That's going to break and put the electrons there. And so what is that going to generate for us? We're going to have this species right here. So we'll have our iron. And now 4 bromines around it. The iron is still going to be negatively charged. But now what has happened to the charge of this bromine, which is that bromine? We just added 2 more electrons there. So that bromine now is going to be neutral because it has the 8 electrons around it, 2 electrons in that bond, and then 2 lone pairs. But what else did we generate? We generated a species that looks like that. A bromine that is positively charged. And that right there is a very strong electrophile. So this Br plus is being represented by the E plus in the general mechanism. And now that we have this piece, now we can bring in our benzene. Okay? We can now bring in the benzene to that we can work with the benzene here. Okay? So what we're going to do is a electrophile. Sorry, an electrophilic. Is there two L's? No, there's just one. It's my bad eyes. Electrophilic addition. Okay. And so let's draw ourselves a benzene right here. Put it above this arrow. So what's an electrophilic addition? Those pi electrons are going to come and attack the electrophile like that. That's going to give us the bromine right there. There's already originally a hydrogen, so the hydrogen is still there. That hydrogen is there. That hydrogen's still there, but that carbon only has 3 bonds. Hence, that's why we have a positive charge. And then what we're going to do is this next step is not reversible. This is the electrophile elimination. There's our electrophile elimination. And how does that work? Okay. And that is a base is going to come in and abstract this proton. So what base do we have here? This, right there. That can behave as our base. So we're going to use one of these iron-bromine bonds, right, and that's going to come and abstract that proton. And then it's going to put the 2 electrons in between this carbon and that carbon. And that's going to restore aromaticity. Like that. And then what did we generate here? This bromine grabbed that proton. So now we're going to have HBr. So we have HBr present. And what did this piece get? So this bromine is that bromine. But we also have the iron tribromide. We have those 3. 1, 2, 3, which is accounted for right there. So at the end of the day, you're going to have this piece, some acid, and our Lewis catalyst, which has now been regenerated. Because we understand that catalysts are not consumed in a reaction. So we regenerate that. And so I challenge you guys to go back to the electrophilic aromatic substitution general mechanism and see that we have the electrophilic addition and the electrophile elimination. That part matches, right? We just have to envision this positively charged bromine as the E. And then everything right here is how did we get this E? Right? And we've seen these reaction mechanisms right here, coordination and heterolysis. I want to add something to this halogenation reaction. Let's envision if we use chlorine. If we use chlorine, we also need a Lewis acid in order for it to work. And you can see that I chose a different Lewis acid this time, aluminum trichloride. And so if you want to put a bromine on the benzene ring, then you're going to need iron tribromide. That would get us a bromine here. But if you want a chlorine, then you use aluminum trichloride. Okay? But the mechanism is so similar. Just change all of this right here from bromines to chlorines and change the iron to aluminum. Change these bromines right here to chlorines. Same mechanism arrow. Same mechanism arrow all the way through. Now, what about adding fluorine? All right. Could we do that? And find a Lewis catalyst that would work for that, Lewis catalyst. And the answer is no. This is just too, well, it will react. It's just very exothermic and you can't control it. And so it's just not a useful reaction. So to add a fluorine here, we're going to have to learn some other reactions to make that happen, but we're not doing a halogenation. All right? So for this reaction, halogenation, fluorine, out. We don't do it. Okay? We would have to do a completely different mechanism and a different reaction. Well, what if you wanted a iodine right there? Can you do that? And you can, but you have to use other reagents as well. Okay? And so you could use elemental iodine right there, and you would have to use a different type of catalyst. You would use our copper, which chloride right here, peroxide. If you use those two or one of these catalysts right here, you can get this thing to work. But it's not the mechanism that I've taught you here. All right. So what you can sum up here is for this reaction, electrophilic aromatic substitutions, doing halogenations, it's only for elemental bromine and elemental chlorine. Those are the only two that are going to work. But if you want a fluorine on there or an iodine, you have to do a different mechanism. Okay? So it's still possible.